Hope that you guys are having a spectacular day. Um, I'm going to begin sharing my screen right now. Um, I wanted to, like I said previously, I would let you guys know whenever Top Hat was going to be ready, and we'll have Top Hat beginning on Friday. And those are going to be your participation points. So come to class, be ready to answer Top Hat questions. That will help with feedback, and I hope that will help you guys. That's why we're going to do them. So with that said, there's not a lot that you need to do. Top Hat is on Canvas, and you also have the app that you can use to answer Top Hat questions. Um, you don't have to register, or I don't think that you have to do anything to register. I did not see a place to submit the note card we were able to use in the exam. Nope, don't worry about it. Yeah, so don't worry about that. All right. Does anyone have any specific questions? I got some private messages. If you have a private message, if you wouldn't mind waiting for a little bit, maybe till the end of class or something like that. Or that might be a good thing to email me. If you have a general question, let me know. With respect to the exam, I have not looked at the average of the exam. What I'm going to do and what I try to always do is basically do a recorded video where I walk through the exam and I talk about the different topics that were discussed on it and provide you with here's the correct answer, here's the incorrect answer, and maybe here's why an answer was correct. And then once I do that, or the reason that I do that is that's also my mechanism to like proofread and check my exam a second time. Um, so sometimes that means I made a mistake on an exam and I'm going to give you guys, and I'll make that correction. I'll give you the points back on that. But with that said, I hope to have that done by the end of the weekend. I haven't had a chance to do that yet, and I hope to do that by the end of the weekend. But in the meantime, what we're going to talk about today is we're going to talk about water. And with respect to water, I want you to be able to list and describe properties of water, predict whether a molecule or part of a molecule is nonpolar, polar uncharged, or polar charged. Identify various bonds and be able to rank their relative strengths, discuss why weak non-covalent interactions, although weak, are useful in biological systems, and describe the hydrophobic effect and its thermodynamic driving force. Be able to identify an acid in its conjugate base or base in its conjugate acids and write balanced chemical reactions with water. Understand acid-base properties and how an acid or base changes as pH changes. Calculate the pH of a strong acid or a weak acid. Determine the concentration of an acid needed to achieve a certain pH value. Generate a titration curve given pKa values. And explain the role of buffers in living organisms. Now, if you're looking at this and thinking, wow, this is lots of Gen Chem 2 stuff, you're pretty much right. It is lots of Gen Chem 2 stuff. The foundations from Gen Chem 2 are going to be important because what we'll use this for is we will use this for gaining a strong understanding of amino acid structures and how those change. And when you understand amino acid structures, then what you can do is you can look at protein structures because everything is in this class is very scaffolded. You learned this so that you can learn this, so that you can learn this, or maybe not scaffolded, but a little bit more stepwise. So this is where we're going. Now, if we think about a molecule of NaCl, NaCl is an ionic compound. NaCl is a strong electrolyte, meaning that it's going to dissociate into a sodium ion and a chloride ion. And if you think about NaCl in a solution of water, well, those ions are going to separate from one another. And if we look on the left-hand side here, we have a sodium ion. And then on the right-hand side, we have a chloride ion. Well, these partial charges of our water are going to be attracted and kind of all coordinate around that. Sorry about that. around that partial positive charge. So here we go. Then in our other ion, we have partial positives of our hydrogen in our water molecule that are going to be positioned in a specific way. So that's how that's going to become soluble in a solution of water. So that's sodium ions and chloride ions. Nothing really new there. Now, we also have other compounds. They're compounds that are, we think about methanol and ethanol and propanol. These are all alcohols. Now, these alcohols have an infinite solubility in water, meaning that you can add those to water and they're going straight into that solution. And that's because we have this hydroxide group that makes hydrogen bonding capable. Now, as the molecule kind of shifts from being, or it shifts so that a lower percentage of it is capable of hydrogen bonding, well, then more of that molecule is going to kind of dictate its solubility. And so what we've got as we get to something like heptanol, 7 carbons in a hydroxyl group, well, that's not going to be nearly as soluble as something like methanol. Now, as a little bit of a review of bonding, there's a couple of bonds that we need to talk about. Most of what we're talking about is not so much the intramolecular forces, but really we're much more interested in intermolecular forces, your IMFs. And so your IMFs that are relevant are going to be charge-charge interactions, hydrogen bonding, hydrophobic interactions, and van der Waals interactions. These van der Waals interactions you might also know as LDF or London dispersion forces. Now, with these charge-charge interactions, you have a positively charged entity and a negatively charged entity, and they're going to be attracted to one another. And they're going to be attracted to one another with a little bit of a range in terms of their strength, 40 to 200 kilojoules per mole, or hydrogen bonds, 25 to 30 kilojoules per mole. Okay, so your charge-charge interactions are considerably stronger and can be much stronger than your hydrogen bondings, even in your strongest hydrogen bonds. Your hydrophobic interactions are basically, I always kind of rank these as 10% of their predecessor. So a charge-charge interaction, well, hydrogen bonds are about 10% the strength of those. It's not a hard line. Yes, it's 10%, but I always kind of think about it as a range, an average. So 10% of, I'm going to label this as CC or charge-charge. Hydrophobic interactions are about close to 10% of the strength of hydrogen bonds. And then your weakest are those London dispersion forces or your van der Waals interactions. Those are going to be considerably weaker than your hydrophobic interactions. So we've got this variable, this strength that we see in all of these. Now, with that in mind, the interesting thing is that all 4 of these are very important for biological systems. If there's 3 of them that are maybe the most important, they would be your charge-charge interactions, your hydrogen bonds, and your hydrophobic interactions. Now, I know that you guys have taken Gen Chem 1 and Gen Chem 2 and organic, but when we talk about hydrogen bonding, obviously hydrogen is one atom that is needed. Go ahead and add to the chat, or I would love for somebody to speak up and say the atoms that are another atom that is involved in the hydrogen bonding.
Fluorine or oxygen.
Fluorine or oxygen. Okay, and somebody else, what's another atom? I'll give you a little bit of a hint. It's on there. That's on the screen.
Nitrogen.
Somebody else. Those 2 voices from one person? Suspicious. Okay.
That was not one person.
That was me.
Oh, there's 2 people in one account. That's what okay. Nitrogen. Okay, great. So fluorine, oxygen, and nitrogen are our atoms that we're most interested in. And somebody other than that account add to or speak up or add what is the property that we're kind of interested in there? You can add it to the chat. What makes those? Electronegativity is absolutely right. So whenever it comes to hydrogen bonding, we can develop a very dense and strong hydrogen bonding network. So hydrogen bonding in a strong hydrogen bonding network, would anyone care to add what are the kind of some of the properties that we know about water that result from its hydrogen bonding network? We've got surface tension is one, high boiling point. That hydrogen bonding network is what gives water some of those very unique properties. And that's worth noting because it's a very high number of hydrogen bonds that aren't extremely strong. Because if you look at this, your hydrogen bonds are weaker than your charge-charge interactions, which are typically weaker than your covalent interactions. So these weak interactions actually have a huge result on the overall strength of or some of the properties of water. Now, we also have to give it to not just those weak interactions, or sorry, when we elaborate on those weak interactions, here are some examples of those. Yes, it is. So we have glutamic acid and arginine. These are two amino acids, two of our proteinogenic amino acids, and these charge-charge interactions between those R groups, here's a negatively charged carboxyl group, and here's the positively charged R group of arginine. Well, those interactions they stabilize an overall force, and they are a stabilizing force between these two groups and in protein structures. So protein structures are influenced by charge-charge interactions. Guanine and cytosine. These are two nucleotides in a DNA molecule that we're ultimately going to come up with 1, 2, 3 hydrogen bonds between them. Whenever we look over at a molecule like here, what we have here, these are two polysaccharides. These two polysaccharides like to have hydrogen bonds between those groups. And then if we look down here in this last grouping, and we look at this chain right here, and this chain right here, and this chain right here, well, these are all hydrocarbons. So what type of interactions will those hydrocarbons likely participate in when they're in contact with one another, or when they're near one another? Absolutely, you've got hydrophobic interactions. Great job. So hydrophobic interactions are going to draw those two together, or draw all of those groups together. Now, that's ultimately going to lead to what's known as the hydrophobic effect. Hydrophobic compounds, polar or nonpolar, these are soluble in water or nonpolar solvents. So hydrophobic compounds in water, they're basically not going to like being around one another. But in a nonpolar solvent like hexane or something like that, they're going to be perfect. They're going to be completely soluble or considerably more soluble. Now, what water tends to do is it tends to minimize the contact with hydrophobic molecules. This is the definition of the hydrophobic effect, where hydrophobic molecules, minimize contact with hydrophobic molecules. The transfer of nonpolar molecules away from water to other molecules is a spontaneous reaction. So that's going to be a negative delta G. Now, to visualize what that hydrophobic effect looks like is we have multiple nonpolar molecules. And these kind of have this, if this blue solution is additional water, that blue shading is water. these nonpolar molecules basically have this kind of encapsulation, and then before too long, they're going to be driven together. And they're going to aggregate together, and there's going to be basically a water shell around those. Now, water reaction, or water is going to react with water as well. So in an aqueous environment or in a solution of water, water reacts with water to produce a hydronium ion and a hydroxide ion. Now, that's something that we have looked at in Gen Chem 2, a KEQ for that, or an equilibrium constant for that. And when you look at that KEQ, you ultimately come up with basically a pKa, because that's our ionization constant for water. Now, to understand the pKa and the significance of a pKa is going to be a measure of, well, this is your Ka. So it's the ratio of the concentration of protons, concentration of your deprotonated form of a molecule or your conjugate base, over the concentration of a weak acid. Now, this is all valuable because what this is going to allow you to do is understand one of the other important properties of water, and that is, or of any solution, and that is the pH of that solution. So we see this with what's known as the Henderson-Hasselbalch equation, where we can look at the hydrogen ion concentration, that being equal to our Ka, our dissociation constant of an acid, times a ratio of our concentration of our acid over our conjugate base. You can take the negative log of that and come up with this equation right here. pH is equal to pKa plus log of your deprotonated form of a molecule over your protonated form of the molecule and the concentration of those. So this is an important thing for you to understand, because what we'll do a lot of in this class is we'll basically look at a solution. We'll look at, let's say, let's go with, lactic acid. Lactic acid right here. One of the things that I think people have a tendency, or that I've noticed over the years in teaching this class, is that there's a common mistake that people make, in that they look at this lactic acid and they don't understand that this form that's written out here is the protonated version of this. Now, the deprotonated version of this molecule is going to be your A minus. So that is CH3, CHOC, sorry, CHOH, COO minus. So these two different forms are protonated and are deprotonated form of our molecule. So at any given pH, we're going to have a ratio of those two things. When our pH is equal to our pKa, which our pKa for lactic acid is 3.9. When our pH equals 3.9, we have an equal concentration, or 50% this, 50% this form of our molecule. Now, if our pH is lower, what do we have a greater concentration of? If our pH is, let's say, 3.5, what do we have a greater concentration of, the protonated or deprotonated form? If our pH is, let's say, 3.5, then we actually have a higher concentration of the protonated form. Because at a lower pH, what do we have a ton of? The pH equals, actually, no, skip that. We have a higher concentration of protons. That's absolutely right. So everywhere that a proton can go, it's going to go. Everywhere on a molecule that can take on a proton, it's basically going to go. So if our pH is 3.5, which is lower than 3.9, then we can kind of look at this almost as, let's say that we've got about 35% of the molecule is deprotonated and 65% is our protonated form of the molecule. So that's something that I've always noticed that it's a concept that people have a tendency to get and make little mistakes on. But I do my best to always think about it as, where am I relative to the pKa? If I'm lower than my pH, or if my pH is lower, that means I've got a lot of protons. So I'm going to pepper those wherever I can. Now, what this is relevant to is, and here's our pKa for something like acetic acid. The pKa of acetic acid is 4.8. Now, if you have a solution where the pH is 4.8, that means you have an equal concentration of your protonated, which I always like to write this as HA, and your deprotonated form, which is going to be your A minus. Okay, so you've got an equal concentration of those two things. Now, if we go over here, well, we've shifted it to the left. So now we've shifted on our curve to the left, so then we have a higher concentration of that CH3COOH. Now, this is based on this titration curve. Is this a mono, di, or triprotic acid? It's a monoprotic acid, exactly. Now, what we'll talk about in this class, and what this is all really, this is all largely review type of material. What we're going to get into is amino acids. Amino acids, every single amino acid, if we think about those terms, amino, we've got an amine group. Is an amine group ionizable? It is. So that's one proton. And then an acid, that acid is a carboxylic acid. Is a carboxylic acid ionizable? It is. So every single amino acid, by virtue of having an amine and an acidic group, these are both ionizable groups. Every single amino acid is a diprotic acid. At least. There are some amino acids that are triprotic acids. Then amino acids can undergo tons and tons of different modifications to make them hexaprotic, but we're not going to get into those. We're going to be staying kind of at the base level of talking about di and triprotic amino acids. Now, you're obviously not going to have to draw a titration curve, but questions that I will give you on quizzes and exams about amino acids will basically be looking at titration curves and pointing to a certain spot on a titration curve. What is this? What is this? So with that said, if we wanted to draw a titration curve or look at a titration curve for a weak acid, here what we have is phosphoric acid. Phosphoric acid is a triprotic acid because it has 3 protons. Now, what this titration curve is going to look like, what we need are our pKa values. Those aren't negatives, those are just little star markings. Okay, our y-axis is going to be pH. Our x-axis is going to be OH equivalents. Notice on the previous slide, they were labeled as the x-axis is an OH equivalent. So these equivalents are, well, 50% of the necessary hydroxides have been added to deprotonate this molecule, or 50% of that molecule, 50% of that proton has been removed through, it has been deprotonated. Then over here, you have reach an endpoint where 100% has been deprotonated. Now, what that means when you talk about a di or triprotic acid is your x-axis is going to be labeled like this: 0.5, 1.0, 1.5, 2.0, 2.5, and 3.0. Now, what's significant about this is it's not important that you or don't get distracted by the, oh, well, what's 2, what's 3? Instead, look at this 0.5 as we're in 50% deprotonated, and then this whole number where it's 100% deprotonated. So what I'm going to do to continue populating this is I'm going to find my my y-axis. This would be my pH. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There. I'm not going to go to 14 because I don't need to go to 14. So my first 0.5 is going to align with roughly my y-axis that would read 2.2. My 1.5 is going to correspond to approximately 7.2. I'm going to put that roughly here. And then my last one, my 12.7, my third pKa value is going to correspond to my 2.5, and that's roughly right here. Okay. Now let's look at this previous titration curve. And give me a word to describe it. You guys know it as the buffering range. But if you were to describe the buffering range of a titration curve to somebody who doesn't know anything about chemistry, how would you describe the shape? How would you describe that line? Tangent line, great. I always like to, I always kind of simplify it for myself as a horizontal region. So we've got 3 tangent curves or horizontal regions here, here, and then here, and here. Okay, so what we've got is a curve that looks like this. And this is a little bit shaky there. But essentially, that's what we're looking at with respect to a titration curve for a triprotic acid. Now, the question, or the sort of question that I always like to ask is, let's say that I'm going to refer to these as forms A, B, and C. Phosphoric acid, dihydrogen phosphate ion, the monohydrogen phosphate ion. Now, A is going to be and this is an important term, predominant. A is going to be the predominant form right here. I'm going to draw a dashed line. I always like to draw dashed lines. Yeah. A is the predominant form up until my pH is 2.2. When my pH is 2.2, I have a mixture of A and B. B is my predominant form within this range, from a pH of 2.2 to a pH of 7.2. And then my predominant form C is going to be most common from a pH of 7.2 to 12.7. And then what does the last form look like? At a pH of what's the last predominant form? Let me rephrase that. PO43 minus, that's absolutely right. So that PO43 minus is going to be the most common form at a pH above 12.7. So this is going to be like your most important thing for understanding triprotic amino acids and being able to recognize the titration curve and understanding, the important or the predominant forms. Another thing that we're going to get into is, well, our phosphoric acid. That molecule is triply protonated. And this is where they have a tendency, or mistakes have been made historically. This is a protonated form of a molecule, but what's the charge of it? 0. H2PO4, the charge of that, it's deprotonated, has a -1 charge. And then HPO4 2 minus has a -2 charge. And I bring this up because one thing that I've noticed is that when you say protonated, it kind of implies, oh, it has a proton. Protons have a positive charge. Protonated sometimes might mean that that molecule has a positive charge, but other times it doesn't necessarily. So you have to be kind of aware and thoughtful of those instances where, what does that mean? So with this in mind, this molecule right here has a buffering range, or these molecules, let me rephrase that. These molecules have a buffering range from plus or minus 1 pH unit from the pKa. So it can buffer, it can hold a pH, so you can add acid or base to it and not dramatically change the pH, anywhere from 1.2 to 3.2. And dihydrogen phosphate from 6.2 to 8.2. Monohydrogen phosphate, 11.7 to 13.7. So this is a molecule that can buffer in 3 different ranges. And that's important to know if you're ever working with if you're trying to purify a protein or something like that, and you want to characterize it, well, a phosphate, if that protein has is most functional at a physiological pH, then phosphate buffer is going to work perfect for that, because that phosphate buffer will hold a pH it will hold a pH at 7. It will hold a pH as low as 6.3. It will not hold the pH if you try to adjust it to 5, because then if you add water to it, the pH is going to change pretty dramatically because it doesn't buffer in that range. Okay, well, that's what I wanted to get through today. I'm going to stop my share. Then what I'm also going to do is let's see, today's Wednesday. So on Friday, we're going to start talking about amino acids. And if you feel good about titration curves and understanding what information is in a titration curve, then you're going to be in good shape for understanding amino acids. Then it's almost just a matter of, okay, well, I've got to get more familiar with the structures, the amino acid structures, and how can I kind of shoehorn those or modify those or understand my modification of those molecules for the purposes of titration curves. In the meantime, though, I'm going to stop my recording. If anyone wants to hang around, you're more than welcome to. I can answer some questions, or if you want to discuss something in private, I'm more than glad to